SwayamPrabha. Digital India. Educated India.
How do you make air conditioners noiseless? This is supposed to be split AC, is it? No. It is not window. It is only split. I think it is better than, supposed to be better than split. Split will not give, as I said, window when compared to window. Central AC, if you put, you will not have any noise. Start. Okay. Yeah, I think yesterday what we have discussed about fluidized beds, you remember a little bit? Yeah, come to the class, I say. Okay. Mentally. Okay. So we have discussed the definition of fluidization and types means what types we have discussed? Regimes and all that we have discussed. Good. Yeah. Now to design fluidized bed reactors, what are the parameters we should know? That is what we are going to list here. Number one is particle size and fluidization characteristics. Fluidization characteristics. Number two is pressure drop due to solids, or sometimes you can also say bed. Pressure drop due to solids in the bed. Okay. So number three is pressure drop due to distributor plate or distributor, and number four is minimum fluidization velocity. Number five, terminal velocities. Six, bed height. I think I will write here static bed height. Seven, heat and mass transfer correlations. Yeah, the last one, 8, is, oh my God, difficult to write. Reactor models. Yeah, reactor models. See how many things we should know, and actually this is a full course if you teach all of them one by one deeply. Good. Yeah, but I think all the points we will just touch, and this we have to go a little bit deeper just to develop the model. So, you need to find out what are the particles that can be used for fluidization. What kind of fluidization you get if you use different size of the particles, that is one. Number 2 is that the pressure drop, how much maximum pressure drop that will be there for the solids, okay? That is one. Then you have the distributor to support the solids, right. So, what is the maximum pressure drop this distributor plate should have? How do you design this distributor plate? That is very important. So, then like for example, what is the free area we allow? When you have the distributor plate, you have perforations, and what is the area? Is it 100%? 100% means same column diameter. So, then 50%, 70%, 80%, 30%, how much you go for free area? So, that is what you have to also find out, and that correspondingly gives you the pressure drop, that is the one. Then we have the minimum fluidization velocity. I think I better write here this symbol UMF, right. So, that is the starting point of the fluidization. Then we have terminal velocity of the solids. Actually, it does not have any meaning here, terminal velocity. We are talking about single particle terminal velocity, where in the bed you have lots of other particles. So, in the presence of other particles, definitely the terminal velocity will be different, but even then we would like to have an idea what is the maximum upper side what you can go, but sometimes even plus or minus 100 times you will go around that velocity. Okay? Yeah, because multi-particle systems even now it is very difficult to characterize, and there is no theory where you can get all the solutions using from first principles and also closed form solution. Closed form solution means correctly you are having the solution, you have the nice equation, and when you solve it as a differential equation first order for example, you will get a nice solution. All that is not possible for multi-particle systems, and that too in the presence of some other fluid, either gas or liquid. So, then you have the static bed height. What is the bed height to start with you have to take? We discussed it at HP, height of the packed bed before fluidization. What it should be? How many times L by D for example, or how many times D? If I take 1 meter diameter, how many times I can go as packed bed, static bed before starting fluidization? 2 times, 5 times, 10 times. Okay? So, that also is important for us. Then you have heat and mass transfer correlations, both will take place. I think during reaction you have either exothermic reaction or endothermic reaction. So, heat transfer will automatically come into picture. Catalytic reaction, so mass transfer again comes into picture. So, that due to diffusion the reactant gases have to go into the catalyst, get reacted, come out, all that things. Okay? So, that is what is heat and mass transfer correlations what we have. Then finally, we have the reactor model. Okay? What kind of reactor models we have? Ideally only 2 flow systems, PFR and MFR. Okay? So, we have to also see which one is more suitable here, either PFR or MFR or both. That is what is the overall picture. I think I have to complete all this in 2-3 classes. So, that is why first let us take this parameter, particle size and fluidization characteristics. Yeah. A lot of all these things are mainly empirical, and many researchers try to find out what kind of fluidization you get if I take for example 10 micron particles, 100 micron particles, 1000 micron particles, 10,000 micron particles. Okay? Generally beyond that we do not go, beyond 1 micron, 1 particle itself, beyond that we do not go 1000 microns, but still there are large scale fluidization particles where particularly fluidized bed combustion they use around 5 to 6 coal particles, because they cannot go to very fine powder. If they go to very fine powder, all the energy what they produced in the thermal power plant will be used for crushing, because tons and tons of coal has to be crushed to very fine powder means. Okay? So, that is why practically they found that around 5 to 6 size coal combustion for coal combustion. So, I think beyond that normally we do not use the fluidization operation, that is the maximum, right. And if you want to use beyond that also some kind of good contact, then what we call it as spouted beds, spouts. The bed, heavy large amount of large diameter particles will spout rather than entire bed moving. That I think also I will mention when you are talking about this. So, that is why many people tried, and then they try to give the good fluidization. For example, good fluidization means where you have smooth uniform fluidization, like particulate fluidization. Particulate fluidization is good fluidization. Why? Because interparticle distance is same everywhere. That means all particles are uniformly distributed in the bed, nice things happening. Okay? Like Western society where discipline is there. Okay? Yes, to some extent there is discipline there, not like our traffic and all that. But whereas here in the real aggregative fluidization, excellent representation of India. Chaos, you cannot find out. Suddenly there may be bubbles, suddenly there may be bubbles bursting, suddenly there may be bubbles starting, and in between there are good ordered people in between, somewhere this corner one, this corner one, the other corners one. So, that kind of chaos will be going on. So, that is why some of them try to put this information in terms of dimensionless numbers. Obvious first dimensionless number that will come is Reynolds number. Very good, good guess. So, afterwards that only we know. Next one. Next number you tell me. Savita? Sherwood number will not come here. This for fluidization characteristics. Sherwood number will come in this step. You are playing chess, thinking 10 steps ahead. Okay. We are talking about only that particle and fluidization characteristics, where we are not talking about heat transfer, mass transfer, anything. Any other number? You see, I told you, actually I am a good person. Why do you scold me? I do not know. I think all the time, my guess, and I am a very good psychologist, I say. I can easily find out how the student's mind will work. You see how much time you are taking to give second dimensionless number in fluidization. It is a fluid particle system. Porosity is not a number, no. It is just a parameter, dimensionless number. Yeah, Archimedes number is 1. Yeah, other than that, for fluidization, yeah, 2. I think you would have never have heard of what is called Froude number, u square by g dp. What does that tell you, Froude number? This is my problem, I say. Once I start discussing, it goes. Okay. Yeah. By what is the definition of Froude number? Equation. To be fair to you, I do not ask Archimedes number, okay, because no one can tell definitely. Can you tell, Narasimha Reddy? Equation. Tell me.
dpq rho f into rho s minus rho g into c by
No into there, only divided by mu square. Yeah, that will come anyway when you are discussing about minimum fluidization velocity. Yeah, Froude number is another number which will come. Okay. So, and of course, friction factor has a dimensionless number also people use. Yeah. So, all these things will come, and people try to characterize in terms of those numbers. Froude number is u square by g dp, velocity squared divided by g. G is the acceleration due to gravity, dp is the diameter of the particle. That will tell us inertial upon gravitational or buoyancy also, you can say. Yeah, okay. So, that is the kind of thing what we have, but they were not very successful. Then there was a person called Geldart. So, from then onwards it is called Geldart classification of solids. Okay. So, he published a paper in powder technology. Powder technology, we have page number 7. Sorry, this is not page number. I want to write page number and saying. Okay. So, this is volume 7, 285 page number 1973. And again they modified this with another person called Abraham Sen, maybe he is PhD scholar. Okay. Abraham son of Abraham. Okay. So, this is Geldart plus Abraham son. So, these two people again published in the same, that is after 5 years I think, 1978. Okay. So, this is volume number 19 page number 133, 1978. So, they slightly modified the old graphs, and then that is slightly more reasonable, because it is an empirical observation. This is very popular because straightforward and easy to use. That is why all our research must be very simple as possible, but not simpler. Like who said that? Einstein. Yeah, your model should be as simple as possible, but not simpler. It's a wonderful statement, no? Yeah, good. So, they have made this one as simple as possible in the beginning, but I think next one they did not, but it is not simpler, a little bit complicated in the sense that some updating, because it is mainly empirical observation. They do experiments, observe, record. There is no theory behind this. Okay? Yeah. So, what they did was, everything they have put in the form of a graph. If you draw the graph, you will get some experience about this. And you will also know how to draw the straight lines. This is rho s minus rho g, normally expressed as grams per cc. Okay, one can also express in kgs. And this side we have d bar p in microns. Okay, microns. So, that is one, and then the scale changes here from 10, I have here somewhere 100, here 1000, okay, approximately 100. This is log scale, this side, and then this side the density change, the density difference. This is mainly for gas solid only. Okay. 0.1 to 0.1 somewhere here, yeah, this is 1, 0.11. So, okay, this may be 2, 3, 5, normally it decreases, no? Yeah, okay. Log scale, initially this one will be larger, then smaller, like that it goes. Actually, it will be 6, 7, like that. Okay, good. So, this is the scale what we have, and then they put their data in this format, like divide the regions. It will start. Okay, this side also I have to put approximately. Yeah. So, this again, this may be 50. This is also 50, then somewhere here I have 500, yeah, 500, yeah. So, this is only just approximate plotting, this is 50, 100, it starts somewhere here, this is a kind of diffusive region. Not so much, yeah. I will tell you what is this later. All this is one region. Then we have around 1000 starting from here. Okay. This is a yeah. This is one region, then we have yeah, okay, good. So, first draw the lines approximately like that, you know, till 1000 ends here, it may start around 50 here or slightly inside 50. So, this also may start around, yeah, this is 500. So, somewhere in between like this. Okay. So, then what he calls is this he calls as group A, this he calls as group B, this he calls as group C, and this group D. Okay. So, now we have to see first of all what is this group C, group A, group D and all that, right. So, group C particles are the cohesive particles. You can see they are smaller size, fine size. See here even around maybe 20 microns, 50 microns, less than 50 microns, and in general it is less than 100 microns. But these boundaries are not exact. I think they put all the data and then try to interpret, but I think I will also give you some sizes later. But generally when you have small particles, you have cohesive powders. One example is talcum powder, what you put every day morning. Okay. I mean, if you have talcum powder will be around 1 micron, 10 microns, I mean less than that, a very fine powder. So, that is an example of cohesive powder. So, that means when you have that kind of powders, as the size is becoming smaller and smaller, the surface energy is more, they come together, stick to the surface, very difficult to fluidize. That means, the drag force which you are going to use to lift the entire bed may not be sufficient sometimes to break the interparticle forces. That is why you will not get uniform fluidization. Some part the particles may fluidize where you have slightly loosened structure there, in some other parts it may not. So, that is why very difficult to fluidize is group C particles, and group A particles are exactly, I do not know whether you have seen the catalyst or not. FCC catalyst is one of the very good examples there, that will vary around 100 microns. FCC catalyst, I will tell you, I think I will also tell you. Then group B particles, and you do not have to write that, I will tell you notes. Group B particles, just listen there. Group B particles are like sand particles. This is an example, okay, so that you will have some idea. Oh, group B means sand particles, and this is the region where all the laboratories in the world, people like us who work in fluidization, we take always only sand as fluidizing medium. Why? You will get good fluidization, and bubbles are also, they are fast bubbles and all that will come there, but characterizable bubbles, all that can happen here to some extent here. Okay. So, that is why if you go to the literature and try to see either heat and mass transfer coefficients or fluidization, minimum fluidization or terminal velocities or whatever, even pressure drops, everything, if you go and see the literature, 99% of the papers will be dealing with only sand. Okay. If they want to increase the diameter, density, for example, sand density how much? I will ask Abhinav. Abhinav, what would be sand density? Not a bad guess. Yeah, still, that is okay. A kg per meter cubed, I understood. But is it correct? Is it higher or lower? Higher. Yeah, Renita, you have any idea? Around 2000. Okay. I think Prabhu will tell 2500. 1800. Okay, it is 2600. You see, this time you have missed it. Always you are trying to go in the middle path, but this time I think you are tripped. That is why I asked when she said 2000, when he said 3000, I said Prabhu is the best bet to get the answer. So, 2600. Okay. So, to see the effect of density, sometimes we use slightly higher density like steel balls, where you have around or iron ore. Iron ore will be around 4.7, that means 4700 or 5000 kgs per meter cube, all that. So, those things we would have used, but most of the time people love to use these particles or these particles. These particles again this side, this is the boundary, this side particles are better, and this side when you are coming to this cohesive side, again fluidization may be difficult. Okay. So, now please take this, I will give you notes quickly. Yeah, group C, we will start with group C. You can now write group C, underline. These particles are very cohesive and fine powders. So, usually around 10 microns, 20 microns like that. Okay. Normal fluidization is extremely difficult for these solids, because interparticle forces are greater than those resulting from the action of gas, normally drag force, right, or greater than those resulting from the action of gas. Full stop there. Phase powder, that is talcum powder, what I said, phase powder, flour, FLOUR, maize flour and all that, flour, and starch, starch powder, starch are typical of these solids. Okay. Now, next one, group C, group B, sorry, group A, we are moving this way, group A. Okay. Group A particles are aeratable, aeration I say, you like aeration, yeah, AERATABLE, aeratable, or materials having a small mean particle size and or low particle density, having a small mean particle size and slash or low particle density in the bracket less than approximately 1400 kg per meter cube, 1400 kg per meter cubed. Okay, full stop there. These solids fluidize easily with smooth fluidization at low gas velocities and controlled bubbling with small bubbles at higher gas velocities. Okay, full stop. FCC catalyst is representative of these solids. Those are the typical powders. Actually, there is a lot of range here, but still we are somewhere around here. Those are the good representation of group A. Okay, next one, group B. The particles are sand like with size range of 40 micrometers to microns. I just write, sometimes micron m also one can write, to 500 micrometers. Okay, that is the normal size range, but there you can see more than that also. These are the typical group. Okay, sand like particles with size range of 40 microns to 500 microns and density range of 1400 to 4000 kg per meter cube. These solids fluidize well with vigorous bubbling action and bubbles that grow large. Okay. Particles are similar to sand like particles, whatever particles you get similar to sand. Next one is group D. These particles are spoutable, large and dense. In fact, not large, yeah, large and or dense combinations. Spoutable, large and slash or dense. Okay, full stop. Deep beds of these solids are difficult to fluidize. Static bed, if you take 5 or 6 for example, okay, L by D. Deep beds of these solids are difficult to fluidize. Full stop. They behave erratically, giving erratically, ERRATA CALLY. They behave erratically, giving large exploding bubbles with severe channeling or spouting behavior if the gas distribution is very uneven. Okay? Yeah, full stop. Drying grains and peas, okay, roasting of coffee beans, gasifying coals and some roasting metal ores are examples of this group. Full stop. For this group, shallow beds are preferred. Okay, shallow beds are spouting beds are preferred. For this group, shallow beds are spouted beds are preferred. Understood now? Good. Okay. Yeah. So, this graph was generated mainly at room temperature, okay, and varying because velocity is not told there, right. It is only the density difference and average size of the particle. Okay. So, normally the flow through the beds are varied from 1 UMF to 10 UMF, for the generation of this graph. Okay. So, that is one, that is why it is highly empirical. Later, of course, I think in this paper or in this paper maybe they also given equations here and also equations for this, but there is no equation here because this is a band where you have that error too much, this side or that side. So, that is why it is drawn like this. Here at least the boundary is sharp, but with again difference between A, B and all that. This gives a beautiful idea. For example, if you have from the process, normally you have a process, okay, mining for example, you took from mining coal particles for example for gasification, and all of them are approximately 7 mm, Okay. Will you know some idea of fluidization, what kind of fluidization you are going to get from this information? Correct, no? That is what we have discussed till now, right. So, if I have 7 mm or 8 mm, or sometimes we dry paddy here only, but in other countries they also dry wheat and all that, roasting of beans. Okay. So, all these are large particles. So, then the moment I have that kind of particles, which is the starting point, then I will know, oh, maybe I will have this kind of fluidization for me. So, I better go for shallow bed. Shallow beds means very shallow. It is if L by D is 0.4 or 0.5 or 0.2, that is shallow bed. Why? Because here for large particles, if you have very deep beds, fluidization is very difficult. And when you are pushing the gas more and more for getting fluidization, suddenly they explode, because you will get exploding bubbles, channeling may occur, particles may be throwing here and there, very high aggregative fluidization, which is not uniform fluidization, right. So, that is the reason why you will have an idea, okay, when I have group D particles, let me go for spouting. Spouting is another very nice operation. In fact, spouting beds alone, there is a book also, they do like this, they have a cone and they have the particles, this is gas introduction. Okay. So, this will go like this, pushing the particle, this is gas. Of course, some amount will percolate also through the bed. So, you see here it goes like this, it goes like this, and some of the particles are caught and again coming here, circulations. Okay. You do not have uniform exposure of each and every particle, but on the average if you take, because of these circulations, this is the circulation what you have, circulation will be like this, like this. So, circulation will be like this, yeah. Because of those circulations, you will have good drying characteristics. But you see here advantage is I do not have to use that kind of very high gas velocities, because that spout only I have to manage, where like UMF you have here spouting velocity. What is the minimum fluidization minimum spouting velocity where the circulation start? Okay. What, Shekhar? Like a fountain, exactly like a fountain, where these solids are going to this, and then near the wall you have the sliding mechanism. So, the entire bed moves like this, this entire bed moves like this, then on the whole you have good exposure for the hot gas if it is drying operation. Okay. Good. So, that is the one, that is called spouted bed. We are not talking about that. We are talking about in case you want to use a fluidized bed, then go for only shallow bed. Shallow bed means if the diameter is 1 foot diameter, probably you have to use only 4 inches, 5 inches, 6 inches. Then you will not have time, or not we will not have time, gas will not have time to become a big bubble, easily it will come out, that is the reason. Okay. Good. So, that is the one. The moment you know that you are in B, group B, then we know that yeah, it is sand like particles, good fluidization, but see the bubbling is vigorous here, here it is exploding bubbles, here it is vigorous bubbles, and here small and smooth bubbles. Which you prefer, this or this or this? This one, because small number of large not small number of large number of small bubbles you will get many, good for us, because that is how the contacting between solids and gas will improve. So, that is why we have, that is why this gives a wonderful picture for us. Of course, there is a lot of discussion again correctly how the fluidization takes place and all that, we cannot go. And I can tell you for example, one here in the cohesive powders, when you want to fluidize for example flour for drying purposes, flour, or what is the other one we have, starch powder. So, what happens is when you are using that, or talcum powder, you have the distributor like this, then you are sending the gas, here you have the powder, that is very fun powder. So, most of the time snakes will form here. What are the snakes? This one, because of the interparticle forces, if there is a weak structure inside, so this will start, it goes like this, that is a snake if you put like this, okay, like this. So, like that here there may be another snake, yeah. But if you go on doing that, all the snakes will become one, because they coalesce together and then you have the fluidization, but that fluidization all the powder may be thrown out. So, that is why you can have a bigger cross section like that, even though if they fall again come back again, okay, safe. So, that is why. So, this kind of possibilities are there if you have cohesive powders. So, that is why that is very difficult to fluidize. Now, with nanotechnology, these people are now trying to use fluidized beds, nanotechnology, nano powders, nano size powders. Okay. And even of course, Japan has done wonderful work on this, particularly when you have cohesive powders, they used very nice techniques. Okay. One technique is vibrating the bed. Yeah. So, the moment you start vibrating the bed, the entire bed with nice vibrations, then snakes will not form. What is that you are trying to do? Only you are trying to loosen the powder by shaking, right. When you are shaking like this, the interparticle forces will be gone, right. So, then easy to fluidize. So, that is why there is no end for human mind, I say. Okay. But only thing is you have to sit down and then think properly. Yes. So, this is what that can be done, and then that kind of thinking should come first in the mind, and then you have do the experiment and prove that your thinking, your hypothesis and what you have done experimentally both are right. If both are right, you are great. Abhinav. Okay. Do M.Tech, I say, beautiful, or MS somewhere. You are doing good. So, very nice, good. So, this is the particle size and fluidization characteristics, that is this. I think still I can tell many things about that, but all stories we do not have time that much. Then this first part is over. Now, second one is pressure drop due to solids, that is simpler one. So, let me quickly finish. So, here I have to draw the picture for fluidization. Yeah. Okay. We have the bubbles. Okay. Somewhere here. Then yeah. So, that is the manometer. Then we may have, this is the manometric fluid. That is the pressure drop which we can measure. Okay. Yeah, pressure drop due to solids we are taking. Good. Yeah. See, okay. What is that you are discussing? Yeah, you have an experiment definitely. The only thing is, I am very happy you are able to recollect that you have the experiment for fluidized bed only or something else. Liquid solid. Why choice? Packed bed, fluidized bed, both are important for chemical engineers. Wait, what is the concession? Yeah, I mean, I was giving 12 means 12, all 12. We had 12 experiments at that time. Okay. Yeah, good. But anyway, I think there is no choice between packed bed and fluidized. Both you should know thoroughly, because I think packed bed is right hand and fluidized bed is left hand for you. Okay. Good. Anyway, so this is what how we arrange. It is gas solid fluidization. Same thing even liquid solid also. When you measure this, you measure the total pressure drop delta P t, total pressure drop. through this, okay, as delta this one. This also gives some pressure drop delta P d distributor plate pressure drop plus delta P s because of the solids that is here, okay, that is weight divided by unit per unit area, plus I also have delta P walls, wall pressure, that is what I measure. Okay. So, what I do is before starting the experiment, that means before putting the solids inside this, then I do the experiment for the same velocities, different velocities, for the same velocities without any solids. What do I get? I get the pressure drop due to distributor plate and also pressure drop due to wall. So, then delta P s I will subtract, delta, to get delta P s I subtract delta P t minus delta P d plus delta P w. Okay. Correspondingly, if I also plot this when I am doing that experiment, I think this also you could have done delta P versus u plotting graph. Okay. Initially, when I have low flow rates, then that is nothing but packed bed, right. So, you may get a linear graph, which is not true all the time, okay. Yeah. And then it will go like this, it goes like that. But if you do not know this, and then if you have plotted the total pressure drop, then what you get is this. This is delta P versus u, like this. I do not know whether you remember your graph now, whether this way you got, that way you got. That is the right one, this is wrong one. Why? Why this is wrong one, that is right one? This is only, which is not fluidized. This is also fluidized. This is, at this point you have fluidization, but after that it is continuously increasing pressure drop. So, after fluidization, our theory is that because there is no more additional solids. So, the total weight is constant, weight per unit area is your pressure, okay. Pressure drop must be constant. Okay. So, that is what is that. This will come because without knowing yourself, this distributor is there. If you are measuring the actually distributor will contribute much more pressure drop at higher velocities. Okay. So, that was added to that, though that is the reason. When I was doing that laboratory in charge, when I was also conducting those experiments for students. So, this kind of graphs they used to plot, then we used to explain no, that is not right, you have to subtract the distributor pressure drop and then only you will get almost horizontal like that. Okay. So, this is the one. Okay, good. So, this is of course, at this point what we call it as UMF. If you go much beyond this, where terminal velocities come, it is pressure drop only we are plotting, then what will happen? Solids will go out, okay. Yeah, then you will get something like this. So, actually this is maybe approximately u t, because solids will go out of the system, that means total pressure drop is less, right. Yeah. So, this will happen. I think I will stop here. I have to develop an expression for this. I think that I think Ravi has become to me also terror. I think he made me like that. Shekhar, want to run? Okay, run. This is delta P s. Yeah. Okay. Even though you write here delta P s, this is wrong. It should be removed, so subtracted. Only this one you have to add. Okay, you leave.